Hi, Math 30-1s. We're going to start into graphs of rational functions today. So what you're basically going to see is that we are going to be bringing together both asymptotes and points of discontinuity. So over the last 2 days, the first day we took a look at asymptotes, and the second day we took a look at points of discontinuity. Today you're going to see that graphs can actually have both, not necessarily just one or the other, depending on what the numerator and denominator look like. Okay, so just to start, under the review, it says if a rational function has a denominator which can be made to equal 0, then the graph will have a vertical asymptote, a point of discontinuity at each 0 of the denominator, which means when you factor the denominators, okay, each factor will basically form some sort of discontinuity on the graph. So again, like I said, okay, here's the first type, asymptotes. Now we're comparing basically the degrees of the numerator and the denominator when we are talking about the horizontal asymptotes, okay? And these 3 points that you see here, 1, 2, 3, were brought up about 2 lessons ago, comparing the degree of the numerator and the denominator. So if the degree of the numerator is less than the degree of the denominator, y equaling 0 will be your horizontal asymptote. Remember, that is the x-axis. If the degree of n of x is equal to the degree of dnx, then we form a fraction using the leading coefficients, okay, of the numerator and denominator. And if the degree of n of x is greater than the degree of the denominator, okay, this will be like the best. That just means there is no horizontal asymptote at all. And then when I move back up here to vertical asymptotes, okay, we're just talking about the non-permissible values of the denominator. Points of discontinuity. This is what we discussed, and you heard me kind of cast yesterday on YouTube. This is where basically when I factor the numerator and denominator, they share a common factor. Okay, so that point right there, very important. The factor that we cancel out will result in an open circle, okay, on the graph at a specific point. Okay, and they will ask again for the coordinates of that point, and the 3 steps there: you factor the rational expression, simplify by canceling common factors, and then substitute the non-permissible value of the factor you canceled out into the simplified expression, and that will give you the y value of your point of discontinuity. Okay, so new stuff for today. We'll start on the next page. Investigating graphs of rational functions with no discontinuity, meaning basically there will be no non-permissible values of the denominator. So that's kind of the first statement that they give us here. It says if the denominator of a rational function has no zeros, okay, so there are no values that can make the denominator equal 0, there will be no discontinuities on the graph, and therefore we would call that graph continuous. Remember, we can draw it without lifting our pen or our pencil. So part 1, they give us the equation f of x is equal to 1 over x squared plus 1. Answer A to F before graphing the function. So does the function have any non-permissible values? And the answer there, okay, is simply just no. The reason being is that if you take a look at the denominator, I have a squared term right there. Now, no matter whether I substitute that x value with a positive or negative value, it will always be positive. And then if I add 1, it's impossible to make that equal 0. Okay. Now state the domain of the function. Well, I can basically substitute any value for x that I want into that equation. So I just say x is an element of the real numbers. Part C says the max value of the function will occur when the denominator has its lowest value. Determine the max value of the function. Well, that will occur when I substitute 0 into the function. So therefore, if I have 1 over 0 squared, substituted that in for x, and then I add 1. Well, we know 0 squared is 0 plus 1, so I get 1 over 1, okay, which has a value of 1. Okay, so that is our max value, okay, that they were asking for at the beginning of the question. Now, explain why the value of f of x can never be negative. Well, basically, like I explained at the top, whatever I substitute in for x in that equation is going to be squared. So all you have to basically say is that both numerator and denominator are positive for all values of x. Okay. Now, again, if you understand that in different words or a different way, then feel free, by all means, obviously write it down in whatever terms make sense to you when you're studying and going through the notes. Does the function have any zeros? Well, no, it does not. Okay, there are no factors in the denominator that will allow me to factor it and talk about discontinuities, so no zeros at those points. F says use the answers above to suggest a possible range for the function. So when we talk about this, we know that f of x can never be negative, right? So that's kind of a key point there. So I'm just going to write that down. So f of x can't be negative. Okay, and since the numerator is equal to 1, the denominator can be any value that is greater than 1. So when we take a look at this, we're basically going to have y values, okay, or your range. Okay, so again, in set notation here, the range is going to be anything between 0, okay, and 1. Now you'll notice when I wrote that in set notation, I did not put an or equal to sign here. Okay, because I know that when I compare the degree of the numerator and denominator, okay, that basically I will have a horizontal asymptote at the x-axis, or y is equal to 0. Part G now says use a graphing calculator to actually sketch it. So remember, when I put this into my calculator, it's 1 divided by, and I want to make sure x squared plus 1 is in brackets. They've been nice to me. They've given me the Windows settings. So remember, it always goes min, max, and scale for both of the x's and the y's. So when we do that, okay, we take our calculators, okay, and I put that in, okay, and I hit graph. Okay, you will see a shape that, like this, okay, reaches a maximum value of 1 right there, okay, and then travels extremely close to the x-axis, comes up, and then kind of comes back down on the other side, like that. So you should be seeing a shape like that on your calculator screen when you use the correct keystrokes and enter the right values using the appropriate window settings. Now, based on what we see and what we know by looking at the equation, does it have a vertical asymptote? Well, the answer is no. One, we can see that by looking at the graph. The other way we know that is that there were no factors in the denominator, okay, that I was able to factor out and find some non-permissible values. So no vertical asymptotes. Does it have a point of discontinuity? Okay, no. One, again, looking at the graph, I don't really see one. But if you remember from yesterday, we don't want to just trust the graph because it might be just one small pixel that's missing from the graph and we might be missing it. Algebraically, how do I know that? Well, there are no factors in the numerator denominator that I canceled out. So it does not have a point of discontinuity. And does it have a horizontal asymptote? Yes, it does. Okay, and that is occurring at y is equal to 0, okay, or again, the x-axis. And I know that by comparing the degree of the numerator with the degree of the denominator. Okay, next page. Okay, so part 2 basically gives us 4 calculator screenshots of rational functions, and again, they give us the window settings there, so min, max, scale for both x and y, and now they're going to ask us questions both on what we see from the calculator screenshots and also taking a look at the equations that are provided for us for each calculator screenshot. So A, and I'll scroll back and forth between the diagrams and the equations so I can explain stuff as we're going through it here. A says state the equation of the horizontal asymptote, if there are any, for each of the graphs. So again, the way I like to do it, since we're talking about horizontal asymptotes, is I usually just look at the equation. Again, you can compare it to the graph, and a lot of the times it matches up, but sometimes there's some discrepancies there, and we'll talk about one here in a second. So the first one, when I take a look at the degree of the numerator and denominator, this is for the first one right here. Okay, my horizontal asymptote is going to be y is equal to 0, or the x-axis, because the degree of the numerator is less than the degree of the denominator. You'll see the same thing for the second one. In the third one, okay, the degree of the numerator and denominator is both 2. So that means the degrees are the same. So I create a rational number or a fraction using the leading coefficients, which in this case is 1 for both the numerator and denominator. So 1 over 1 is just 1. So you will have a horizontal asymptote at 1. And for the last one, there will be none, okay, because the degree of the numerator is less than the degree of the denominator. Now, when I compare those equations I just wrote with the diagrams, okay, you can see that for the first one, y equaling 0, okay, that makes sense, okay? For the second one, that's the one that a lot of times people will have some questions about. The reason being is that we know by definition usually that an asymptote is a line that a graph approaches but never crosses. But if you remember from one of the first days we started talking about asymptotes, horizontal asymptotes are not what we call infinite types of discontinuity, meaning it is possible for a graph to cross a horizontal asymptote, and you can see that in the second diagram right here. It does cross the x-axis, or y equaling 0, but the graph is approaching that from the top and the bottom, both when x is negative and positive. Okay, so again, go off of the equation that's given to you for the function, and for horizontal asymptotes, sometimes there are some strange things that happen like that. In the third one, y equaling 1, okay, you can see that y equaling 1 is right about here. Okay, so that does look like it matches up with what we figured out algebraically, and there are no horizontal asymptotes in the last one. Okay, so that matches up with what we see from the calculator screenshot. B says, do the equations agree with the rules of horizontal asymptotes in the review at the beginning of the lesson? Yes, they do. Okay, the only thing that, again, needed any explanation was that second one, where the graph actually crossed that horizontal asymptote of y is equal to 0. In C now, okay, again, a good question that basically is really representative of what this course is about in terms of notation and understanding what they're asking. So it says, explain y as, and this means as x approaches infinity. So that means as you're traveling along the x-axis to the right, that's positive infinity. The graph of x all over x squared plus 1, so that's the second diagram that they gave us, approaches the asymptote of y equaling 0 from above. But as x approaches negative infinity, it approaches the asymptote y equaling 0 from below. Okay, so we have to explain why that happens. So as x, okay, approaches positive infinity, okay, so on the graph, right, that's basically talking about this. As the x values are traveling along in this direction, okay? So we're traveling on the x-axis in that direction. It approaches the asymptote of y equaling 0 from above. So as x approaches positive infinity, both numerator and denominator are positive, okay? So you can't make them negative because you're going to be substituting in positive values for x. So both numerator and denominator will be positive. Now, as x approaches negative infinity, so if I again go up to that little x and y axis I drew, so this is x approaching negative infinity, going this way this time. Okay, so as x approaches negative infinity, we're going to say the numerator, okay, is negative when you substitute a negative value in, and the denominator is positive. Okay, so we know a negative divided by a positive is a negative. Okay, so the numerator will always be positive when you substitute positive x values in. The numerator will be negative when you substitute negative values in. Okay, so the function changes from being positive to negative when I'm to the right of the y-axis as opposed to when I'm comparing it to the left of the x-axis. Okay, last part D, explain why the graph of x squared over x squared plus 1 has no points in quadrants 3 and 4. Okay, so again, that is going to be the third graph. Well, that basically has to do with that in both the numerator and denominator, whatever x value you substitute into the equation, when you square a value, positive or negative, it ends up being positive. So both numerator and denominator will write here. Okay, so both numerator and denominator are never negative. Okay, so hopefully that makes sense. It's impossible to have either of those be negative. Okay, so h of x, which is the function, okay, is always greater than or equal to 0. Okay, the guy with the fake dot sign says that note that whether or not the graph of a rational function has horizontal asymptotes is not related to whether or not the function has discontinuities. Okay, so again, that point is basically discussing that horizontal asymptotes are not a type of infinite discontinuity. Okay, so again, I've stated that several times, so hopefully you guys can pick up that that's an important point moving forward. Okay, next page. Now on the next page, again, they've given us a whole bunch of functions, 10 of them here, okay? The questions they're gonna ask are all based on these functions. Now, in order for me to answer the questions below, which deal with, when you look below there, discontinuities, asymptotes, x-axis, horizontal asymptotes, okay? Those types of things, we know now, because we've done this for 3 days, that we have to factor those numerators and denominators to see what's happening in terms of, can I cancel common factors? Do they share a common factor? Okay, do they have non-permissible values in the denominator? Those types of characteristics. So the first thing I'm going to do is just go through and actually factor all of the rational functions above and simplify where I can, and then I can go and answer the questions below, okay? Now, when I take a look at a of x and b of x, which are the first two functions there, there's nothing I can do. I cannot cancel anything there. I can't factor. So a of x and b of x are simply as they are. When I move on to c of x, however, in the denominator, okay, you will see that I have a difference of squares there. So I can actually rewrite the denominator as x minus 2 and x plus 2. Okay, so there's that one. D of x, okay, same thing there. We're going to have x plus 2 still in the numerator. The denominator will again be a difference of squares. So x plus 2, x minus 2, but this time I'll be able to cancel the x plus 2's. So I actually end up with 1 all over x minus 2. And I have to state the restriction that x cannot be equal to negative 2 as well as positive 2. All right, e of x, nothing I can do there. Okay, again, it looks like I can factor that numerator, but remember it's x squared plus 4 in the numerator. So that is what we call a sum of squares, not a difference of squares, so we can't factor that. So actually for the first row of functions, only c of x and d of x can be simplified. Now when I move on to the denominator, okay, these obviously are going to be a little more work. I can actually simplify all of these to some degree. So with f of x here, okay, x squared plus 4 in the numerator, that is a sum of squares. So I can't factor that, but the difference of squares in the denominator can be factored to x plus 2 and x minus 2. Nothing that can be simplified beyond that, but I can actually factor the denominators. In g of x here, okay, what I'm going to do is actually factor out a negative from the x minus 4, making that x plus 4. Okay, and in the denominator can actually also take out a negative, and then that becomes x squared plus 4. Okay, and the negatives will cancel that I factored out. It's like negative 1 divided by negative 1. Those cancel, so you just have x plus 4 all over x squared plus 4. Okay, like so. H of x is going to be kind of a similar start to the question. So I'm going to factor out a negative. So this will be x squared plus 4 when I factor out that negative. And in the denominator, again, take out a negative, and now you have x squared minus 4. The negatives that I factored out will cancel. In the numerator, I can't do anything with x squared plus 4, but the denominator is now a difference of squares, x plus 2 and x minus 2. Okay. Moving on to I of x. Okay, hopefully you can see in the numerator we have a difference of squares, x plus 2, x minus 2. And in the denominator, I do have an x plus 2. So I'll be able to cancel the factors of x plus 2, leaving me with just x minus 2. But I do have to state that restriction that I canceled, so x cannot be equal to negative 2. All right. And then the last one here, j of x, okay, a little bit more work here. So in the numerator, I can actually factor out an x squared, leaving me with x minus 4. And in the denominator, I can factor out an x, and that'll leave me with x minus 2. Okay, so the only thing that I can reduce right now is when I take a look at here, okay, the x squared and the x, I can actually cancel an x or reduce an x. So I'll have x minus 4, all over x minus 2. But I do have to remember that x I canceled out as a restriction, so I'll say x can't be equal to 0 as well. Okay, so I've simplified, factored the rational expressions. Now I can move on and answer the questions here that have to do with the questions below, okay? So it says, without sketching the graphs, okay, determine which functions have no discontinuities. So the ones that will have no discontinuities mean that basically there are no non-permissible values in the denominator. So if you take a look at that, that's going to be b, okay, because it'd be x squared plus 4 is the denominator. You can't factor that. There will be nothing you can put in the denominator there to make it equal 0. And the other one that meets that criteria is also g, okay? So b and g have no discontinuities at all. Okay, now no vertical asymptotes. Well, a vertical asymptote is a type of discontinuity, so obviously B and G, okay, will fit those criteria. And then also I, okay, and the reason I will have basically no vertical asymptote is because we canceled the common factors of x plus 2, which just leaves you with x minus 2. So remember, the only way we get vertical asymptotes is when I have a non-permissible value in the denominator that is not canceled out by a common factor in the numerator. Okay. C, no horizontal asymptotes. So when we're doing that, we're comparing degrees of numerator and denominator. So we're looking for where the numerator is larger than the denominator. So in that case, that's going to be E, I, and J. Okay, so those are the three where the degree of the numerator is larger than the degree of the denominator. For D, I want to know where the x-axis, or the line y is equal to 0, is the horizontal asymptote. So in that case, we're looking for where the degree of the numerator is less than the degree of the denominator. So those will be C, D, and G. Okay. Just about done here. With E, a horizontal asymptote with an equation of y equaling 1. So if I want to have an equation where y is equal to 1, that means I'm going to have to compare the degree of the numerator and denominator. The degrees will have to be the same, and the leading coefficients will have to be the same. So I get 3 over 3 or 9 over 9. Okay, those will all reduce to 1. So when I take a look at that, okay, that is going to be A, okay, because they're the same degree. Leading coefficients are 1 over 1. B as well, both but degree 2. Okay, but the leading coefficients are 1. F, you can see in F, they're both degree 2. And in H, okay, so those four will all have horizontal asymptotes that have an equation of y is equal to 1. And finally, points of discontinuity. So with points of discontinuity, I'm checking to see which functions I was able to cancel common factors between the numerator and denominator. So that will be D. Okay, that was the first one. Then I was able to do it in I, and then also in J. Okay, so those three functions will have points of discontinuity. Okay. So hopefully that makes sense, and we'll just move on to this last question, which kind of brings it all together. And this is, a good type of question you would see on a written portion of an exam as a written response question, where they just want to see, can you calculate asymptotes, can you factor, those types of things. Okay, so let's read through it together, and then I'll show you the work. So it says algebraically determine the equation of any asymptotes. Okay, so any asymptotes and the coordinates. Okay, so they want the x and y coordinates of any points of discontinuity on that graph. They also want the domain and the range for the function. So I'm going to start with this over here. Okay, f of x is equal to, I want to factor both the numerator and denominator. They've been nice to me, and they factored the numerator, 2x minus 1 over x minus 5. Okay, but the denominator, okay, is going to be a product and sum multiplied to negative 15 add to negative 2, so that'll be x plus 3 and x minus 5. Okay, those two values multiplied to negative 15 and add to negative 2. So when I take a look at that, they do share a common factor of x minus 5, which I'll be able to cancel out, okay, which simplifies my function to be 2x minus 1 all over x plus 3, okay, where again I have to not forget about what I just canceled out, so I'd say x cannot be equal to 5, okay, and there you go. Okay, so that's basically the simplified version of the original function that they gave me. Okay, so what we want to do now is we want to talk about the asymptotes and points of discontinuity. So if I talk about, let's say we start with the vertical asymptotes, okay? So vertical asymptotes occur at the non-permissible values of the denominator. Well, all that's left now is this x plus 3. Okay, so that means I'm going to have a non-permissible value of negative 3, so that's where my vertical asymptote will be. X is equal to negative 3. Okay, the horizontal asymptote, okay, well, when we talk about horizontal asymptotes, those occur when I compare the degree of the numerator and the denominator. Now, they had factored the numerator already, but when I actually expand those binomials, that numerator here, okay, would actually be 2x squared minus 11x plus 5. So it actually is a degree 2 function. And the degree of the denominator is also degree 2. So I would create a fraction using the leading coefficients. So it would be y is equal to 2 over 1, leading coefficients, which just simplifies to 2. So your horizontal asymptote is occurring at y is equal to 2. Okay, now the last thing I want to discuss here is the point of discontinuity, and then we'll go into domain and range. So the point of discontinuity comes from the factor that I canceled between the numerator and denominator, and that was x minus 5. So the point of discontinuity is going to actually occur at an x value of 5. So remember, what I do there is I take that value of 5 and I substitute it into the remaining simplified function. So it'll look like this: 2 times 5 minus 1 all over 5 plus 3. So 10 minus 1, that's 9 over 5 plus 3, which is 8. So there's your y value. Okay, so your point of discontinuity, therefore, occurs at 5 and 9 over 8. Okay, so that's where your point of discontinuity occurs. So now, real simple for your domain and range. Okay, so the domain, we're going to say what the x values cannot be. So we know the x values cannot be -3. Okay, that comes from your vertical asymptote, and it cannot be 5. That comes from the x coordinate of your point of discontinuity, and then you say x is an element of the real number system. For the range, okay, so the y values, again, what can y not be in this question? Well, there were two values. Y cannot be 2, okay, which is the horizontal asymptote, and it also cannot be the y value of the point of discontinuity, which is 9 over 8. And y is an element of the real numbers. Okay, so that's the end of the lesson. Again, key points today, just that a function can have both points of discontinuity and asymptotes. So just be on the lookout for that. Always factor the numerators, denominators, cancel your common factors, and always state the restrictions in your domain and range. Okay, thanks you guys. We will chat soon.